Hello everyone, welcome back to the channel. So today we're gonna discuss supervised classification again. And before we start writing the code, let's first understand the complete workflow shown in this diagram. So let's discuss the diagram one by one. So we're going to use random forest algorithm for remote sensing image classification. So random forest is a supervised machine learning algorithm that combines the prediction of multiple decision trees to produce an accurate and robust land cover classification. So instead of relying on a single tree, random forest builds many independent trees and determine the final class using majority voting, and which improve the accuracy and reduces overfitting. So let's discuss the random forest one by one. So the process begins with a satellite to multispectral image having a spatial resolution of 10 meter. The algorithm does not use only RGB image. Instead, it extracts multiple predictors variable of 10-meter resolution. The multiple predictor variables such as red, green, blue, near, shortwave infrared, NDVI, WI, digital elevation model, texture feature. These variables contain spectral, spatial, and topographic information that helps to distinguish between land cover types. And next, we have training samples. The random forest algorithm needs the training samples. So the user manually collect polygons or sample points representing non uh, land cover classes such as water, you can see, such as forest, agriculture, bare soil, uh, snow built up areas. Each training pixel already has a non class label, so allowing the model to learn the spectral characteristics of each land cover class types. Okay, the next step is bootstrap sampling. What is it? It's instead of training every tree with the same dataset, random forest create bootstrap samples. So bootstrap sampling means the training data are randomly selected with replacement. And some observations appear multiple times and some observations are not selected. So each bootstrap sample is slightly different from other, like you can see over here. Everyone is different from others. We have 1 to n different bootstrap samples. This process is called bagging, like bootstrap aggregation. And the purpose is to create diversity among decision trees. So that's why we're going to use bootstrap sampling. Then we have multiple decision trees. Each bootstrap dataset is used to train an independent decision tree. Like this, one bootstrap is for one decision tree. Tree 1, tree 2, 3, 4, 5, and up to so on, a lot of trees. Each tree has a different structure, like as you can see. And why it is different? Because it received different training samples. It evaluate different predictor variables. And each decision tree learned different decision rules. For example, so random feature selection over here, one of the most important characteristic of random feature is that not all the predictor variables are considered at every split. Instead, only a random subset of variables is selected. For example, instead of using NDVI, near infrared, shortwave infrared, DEM, texture, slope, aspect, radius, one tree may randomly receive only NDVI, near infrared, shortwave infrared, while another receives DEM, texture, slope. The randomness reduces the correlation between trees, increases the model diversity, improves generalization, and reduce overfitting. And then we have majority voting. How it works: each decision tree independently predict a land cover class. Like this will predict a separate land cover class. This will predict a separate land cover class. So for example, tree 1 is forest, 2 is also forest, 3 is agriculture, 4 is forest, 5 is forest, and 25 is forest. And the final prediction is forest. Since most trees predict forest, the final prediction become forest. And the process is called majority voting. So this is how this algorithm works. Instead of trusting one decision tree, the algorithm trusts the majority of all the trees. And in the seventh step, we have the classified image output. So after all pixels are classified, the algorithm generate the final land use land cover map. standard GIS colors are used, like blue for the water, dark green for the forest, and so on. The map also include the coordinate grid, north arrow, scale, power legends. These are things that we can create in another software like ArcPro, QGIS, or any other thing. Okay, the most important another step is accuracy assessment. So after classification, model performance is evaluated. We start from confusion matrix. The confusion matrix compares the actual classes over here and the predicted classes that are over here. So diagonal values represent the correct classified pixels, and off diagonal values represent the classification errors. We have accuracy matrices, like we have overall accuracy over here, that is measures the percentage of correctly classified pixels, like it if it's 94.25%, that's really good. Then we have user accuracy, like indicate the probability that a classified pixel actually belong to that class, and that is 93.11%, that's also really good. Then we have producer accuracy. It measures how well the classifier identifies reference samples. That is 94.73%. That's also really good. Then we have precision. It fraction of predicted positive that are corrected. We have then a recall, fraction of actual positive corrected detected, F1 score, harmonic means of precision and recall. We have a kappa coefficient. Measure the classification agreement beyond random chances. A kappa value above 0.80 indicate excellent agreement, but it would be good if it's if it's greater than zero point 0.6. Like it's considered as a moderate good, but not really good. But after zero point 0.8, it's considered as a really good. So these were all of the accuracy matrices. Okay, we have here feature importance. Random forest ranks predictor variables according to their contribution to the classifier. In this figure, we have NDVI, near infrared, short wave infrared, texture, elevation, red edge, slope, and DWI spectrum blue. So variables with the higher importance contribute more to accurate classification and are useful in the feature collection. So we have used NDVI most over here. And then we have OB error convergence. The graph shows how prediction error changes as more trees are added. So initially the error decreases rapidly because each additional tree improves the ensemble. Eventually the curve stabilizes at 6.18%, indicated that adding more trees provide little additional benefit. So this helps determine an optimal number of trees. So this is how random forest algorithm work. If you still have any confusion in random forest, you can comment below, so I'll give more details on that. So now let's get back to the code and let's understand it line by line how it works. Okay, so I have already took the points of urban, bare, water, and vegetation points. Remote sensing project is defining the study area. Here we are loading the boundary of the Bangalore city from an Earth Engine asset. A feature collection is simply a collection of the geographic features over here, such as points, lines, and polygon. In our case, it contains the polygon representing Bangalore's boundary. Then we have created a variable where we are just loading the harmonized Sentinel-2 imagery. So here we just load the Sentinel-2 Surface Reflectance dataset. An image collection here is the collection of satellite images captured on a different dates. Instead of one image, now we have access to thousands of Sentinel-2 images stored in Google Earth Engine. Okay, next we have to choose the year. So from where we gonna analyze, instead of writing the year repeatedly throughout the script, we store it in a variable. If we later want to classify another year, such as 2020, we only need to change this year value, and we need to change these of some of the training samples that we're going to use. And okay, so in the next step we have the start date and have the end date. So this create the starting date of for our analysis, which is January 1st of the selected year, and instead of manually entering December 31st, we simply move forward by 1 year. So this makes the script more flexible and easier to use. So this is how it's work. Then we have just applied the filter, the cloud percentage, maybe less than. We have applied the function less than, so it must be less than 30. We have just added the start date and end date and filter it to our geometry. The start date and end date are mentioned over here. Now we load the cloud score plus collection. uh, it's the dataset. Unlike the general cloud percentage of an image, cloud score plus evaluates every individual pixel and tells us how clear or cloudy it is. So this is gonna work something like that, and the line below it checks which band are available in the cloud score plus dataset, so they can be attached to the Sentinel-2 images. This is very useful function. It contains the Sentinel-2 images with the cloud score plus information. Think of it attaching an extra quality report to every satellite image. So here we created a mask pixel with a low CS and a QA score. So what will it do here? We create our on function. A function is simply a reusable block of instruction. We will use this function to remove cloud pixels from every image. And then we have used varq a band CS. This tells us Earth Engine to use the cloud score band called CS. We have created a variable clear threshold zero point 0.5. We set a threshold value of zero point 0.5. Pixels with the score greater than or equal to zero point 0.5 are considered clear enough for analysis. We have created another variable mask. So in this we have used GTE over here. So what its mean is greater than or equal to. If a pixel has a cloud score of zero point 0.5 or higher, it is marked as a good quality pixel. And then we have the return dot image dot update mask. Finally, we apply the mask. Cloud pixels are removed and only clear pixels remain. We have filtered mask all the things, like the map function automatically applies our cloud masking function to every image in the collection. After that, select.b uh, keeps only the Sentinel-2 spectral bands whose names start with the letter B. And then we have created a composite over here. So since we have many cloud tree images over here, we combine them into one image using the median function. So the median composite reduces remaining clouds and create a clean image representing the entire year. And then we have some of the visualization parameters, and we have added the band 4, band 3, and band 2. And then we have map.add layer composite. So now we display the satellite image on the map. So the image is clipped to the study area so that only Bangalore is shown. And then we are merging the training samples. Like we have created a variable GCP. We combine all the uh, ground sample points here. We combine all the ground control points into single collection, and each collection represent one land cover class. After merging them, we have one dataset containing all training samples. And then we are extracting the training data. Like this sample regions function extract the spatial values from the satellite imagery at every training point. And we have defined the collection as GCPs, use the ground control point as the training location. We have the properties land cover. Like copy the land cover labels from each point and tells the classifier correct class of each training samples. We are using the scale 10 because we are using the Sentinel 2 main bands have the spatial resolution of 10, so that's why we're going to use 10. And now we are training a classifier. Like now we train the random forest classifier. The number 50 means the algorithm will build 50 decision trees. The final prediction is based on the combined result of these trees, making the model more accurate and reliable. We are using features as training. So these are the training samples used to teach the model. We are using class property land cover. This tells the model which column contain the correct land cover labels. We are using input properties as a composite dot band names. So use all the spectral bands of the composite image as a input variable. Okay, now we just classify the image, and we're using a variable classified composite dot classify inside classifier. The trained model is now applied to every pixel in the image. Each pixel is assigned to one of the land cover class based on its spectral characteristics. Each class have its own color. We assign color to each class so that classified map is easier to understand. And then we are just adding it to the map. This displays the classified land cover map using the color palette we just defined. And then we have defined some of the extra classes for water, because we want to see water as a separate class. So suppose we are interested only in water bodies. Since the water class has a value 2, that is equals to 2, so the function create a new image where water pixels are assigned a value of 1 true, and all other pixels are assigned as 0. So when I run the code, you will see that the water areas will be colorful and non-water areas will be non-colorful. It may be good. And then in the last line, we are just adding it to the map. This displays only the water class on the map. So the last parameter false means the layer is added but remains turned off until the user choose to display it. And then we have added the here we add the style ground map points into the map, and we are just centering the GCP points into the map. So that's how you can classification your supervised classification using Google Earth Engine. So now let me show the imagery. So this is the imagery of our study area of Sentinel-2. Okay, so here is our Sentinel imagery. So this is the collection image that you can see. It's really clear, and if you want to take the points over it, you can take it easily. Like I can show you the GCPs that I have took in this image. Like here you can see there are the GCPs. These are the water GCPs. These are some build-up GCPs and all other points. Like here you can see the GCPs, and here is the water layer. So the now this is clear that all the water have the one value and all other are 0. Now let's see the classified imagery. So here is the classified imagery. You can see it's accurately classified from all across the borders. So it's completed over here. This is our random forest land use land cover classification. Okay, so this was our classification, supervised land use land cover classification. So that's it for today. If you like my tutorial, please like and subscribe to the channel and turn on the notifications so you don't miss any upcoming tutorial. So that's it for today. See you in the next tutorial.